Okay, so Junior Roberts here with realjuniorroberts.com. Now in this video, we're going to be carrying out an experiment in order to determine the specific latent heat of fusion of ice. Now we're going to be conducting this experiment by using a simulation window to assist us with this experiment. So here we have our lab write-up. So what we're going to do is we're going to start with the write-up, and we're going to go over to the simulation window to carry out our experiment, and then we're going to come back to finalize our lab write-up. So here we have our topic, thermal physics, title specific latent heat. Our aim is to determine the specific latent heat of fusion of ice using the method of mixtures. And we have some apparatus that we're going to be using, which include a styrofoam cup, a thermometer, some ice, a digital balance, a beaker, and a measuring cylinder. Now what we're going to do first of all is we're going to actually draw a diagram of our apparatus. So let me just do that real quick. So here we have our diagram. So we have our digital balance, we have our beaker with an ice cube inside of it, we have a styrofoam cup with some water, and a thermometer. So here is our method. So what we're going to do is we're going to place the empty beaker on a digital balance to record its mass. Then we're going to pour 100 centimeter cube of water into a calorimeter or a styrofoam cup and measure its initial temperature. Then we're going to take one ice cube and place it in that empty beaker so we can obtain its mass. Then we're going to quickly transfer the ice cube from the beaker to the calorimeter, and then we're going to use the thermometer now to stir the mixture until we obtain a steady temperature, and we're going to record all of that information. So what we're going to do now is we're going to actually switch over to the simulation window, and we're going to carry out our activity. Right, so here we have our simulation window. Right, I will include the link for the website to access this simulation. So what we're going to be doing is, as I said, we're going to be determining the specific latent heat of fusion of ice, and we're going to be doing so via the method of mixtures. So here we have our simulation window, and we see that we have some equipment here. So in order to do this experiment, what are some things we're going to do is we're going to actually first set up our apparatus. So we see we have a beaker right here, we have a digital balance, we have a calorimeter, right, with a temperature, with a thermometer. Right, now in the lab, instead of using a calorimeter, we can actually use a styrofoam cup to help us out in this situation. So what we're going to do first of all is we're going to select a solid, and in this case we're going to select ice as our solid. Right, so we're going to select ice, and we're going to use, let us say, 10 grams of ice. Right, so the mass of our ice would be 10 grams, and we're going to allow the temperature to be 0 degrees Celsius. Right, once you have done that, we're going to go next, and that will now allow us to choose the type of liquid that we're going to have in our calorimeter. So for this, we're going to choose water, and we're going to use 100 grams of water. Right, so we're going to use 100 grams of water like that, and we're going to set the temperature to 25 degrees Celsius. right? Roughly room temperature. So 25 degrees Celsius, right? Once you have done that, we can go next, right? Now, what we're going to do now, we're going to start our experiment. And what starting our experiment will allow us to do is we're going to take the ice and we're going to quickly transfer to our calorie meter, right? So once I click start, we're going to transfer the ice and we're going to be able to take some readings. So let me go now. Right, so we have transferred the ice, and as you notice, the temperature of the mixture, it starts to decrease, and that mixture is the mixture of the water as well as the ice. So we're going to monitor and observe when the temperature stabilizes. Right, so we get that the temperature stabilizes at 15.47 degrees Celsius. So what we see is that the mixture of the ice and the water is now 15.47 degrees Celsius. So what we're going to do now is we're going to record the values for the mass of the ice, the initial temperature of the ice, right, the mass of the water, the initial temperature of the water, and the final temperature of the mixture of the ice and water. Right, so that's what we're going to do, and then we're going to do our experiment right up. So we're going to switch over to the screen and we're going to go through writing up the experiment. Okay, so we have obtained our results. So what we're going to do now, we're going to actually fill in our results here. So we saw that the mass of the ice was actually 10 grams. The mass of the water was 100 grams. Right, the initial temperature of the ice was 0 degrees, so we're going to put that in. So this was 100, and initial temperature of the ice was 0 degrees Celsius. The initial temperature of the water was 25 degrees Celsius, and the final temperature of the ice and water mixture was 15.47 degrees Celsius. So we're going to say that the final temperature of the ice would have been 15.47. And similarly, this would also be 15.47 degrees because both the ice and the water achieve this temperature. Now, what we can do now is we can start do some calculations. So it says here that we're to use our results to calculate the specific latent heat of fusion of ice. Now, in this case, right, we can consider that we will have an exchange of heat energy, right, between the water and the ice. So what we can say then is that the heat loss by the water will be the heat that is gained by the ice, right? Because if we look at our results, we see that the initial temperature of the ice was 0 degrees Celsius and its final temperature was 15.47 degrees Celsius. So what that tells us is that the temperature of the ice would have increased. So in order for the temperature of the ice to increase, it must absorb heat energy from somewhere. And in this case, it will be absorbing the heat energy from the water. Right? Also, the temperature of the water, notice that it was initially at 25 degrees Celsius and it went down to 15.47. So therefore, the water would have lost some heat energy. Right? Now, in this case, a couple of things that we have to consider. Now, so the water will lose some heat, but the ice will gain that heat. Now, what the ice will do with that energy, it will actually take some of the energy to allow it to melt, so it can form a liquid. Then it's going to take the remainder of that energy to raise its temperature, right? So what we're going to see now is that we're going to see now that heat loss by the water will be calculated by using the mass of the water multiplied by the specific heat capacity of the water multiplied by the change in temperature of the water. Now, once the water would have lost that heat, the ice would take or absorb that heat energy. And what it will do, it will take some of that heat energy to melt, then it's going to take the remainder to raise its temperature. Now, since we have the ice melting, we will actually undergo a change of state. Now, once we talk about a change of state, we have to talk about a latent heat. Now, in this case, we're going from a solid to a liquid, so we're going to talk about a latent heat of fusion. So it's going to require some heat energy to melt, and we can calculate that heat energy by using the formula where the energy used to melt is equal to the mass multiplied by the latent heat of fusion of ice. So we're going to have the mass of the ice multiplied by the latent heat of fusion of ice. Alright? Plus whatever heat energy we use to raise the temperature of the ice, which is now melted. So, right? So we're going to have mass of the melted ice multiplied by the specific heat capacity of the melted ice, which is water, multiplied by the change in temperature of the melted ice. So we're going to have delta T. Now what we're going to do now, we're going to start to fill in some values. Right? So the mass of the water is 100 grams. So we're going to convert 100 grams to kilograms. So when we convert 100 to kilograms, we're going to get 100 grams to kilograms, we're going to get 0.1 kilogram. So we say 0.1 kilograms, so 0.1 kilograms multiplied by the specific heat capacity of water. Now the specific heat capacity of water is 4,200 joule per kilogram per Kelvin, multiplied by the change in temperature of the water. Now the change in temperature of the water, we can determine that by taking the difference of 25 and 15.47. So we take a calculator and we simply say 25 minus 15.47, and we're going to get 9.53. So the change in temperature of the water would be 9.53. Right, now since we're talking about a change in temperature, right, a change in temperature in degrees Celsius is the same change in temperature in Kelvin, so we can say 9.53 Kelvin. Now that now will be equal now to the mass of the ice, which is 10 grams. We're going to convert to kilograms, so we're going to get 0.01 kilogram. So we have 0.01 kilograms multiplied by the latent heat of fusion of ice, which is what we're trying to find. So let us call this LF, right? So this is LF for the ice plus the mass of the melted ice, right, which is now the water. So it's 0.01 kilograms multiplied by the specific heat capacity of water, because it's the melted ice, so we have 4,200 joule per kilogram per Kelvin, and that now will also be multiplied by the change in temperature of the ice. Now the ice would have, when it was melted, it would have changed its temperature from 0 degrees up to 15.47 degrees Celsius. Right, so the change in temperature will be 15.47 degrees Celsius. Now from here we can start to do some simplification. So we're going to first start by simplifying this portion. So we're going to take the calculator, we're going to say 0.1 multiplied by 4,200 multiplied by 9.53, and we're going to get 4,002.6 joules, and that now will be equal now to 0.1 kilograms multiplied by the latent heat of fusion of ice plus this value right here. So we're going to say 0.01 multiplied by 4,200 multiplied by the change in temperature, which is 15.47, and this works out to be 649.74 joules. Now what we're going to do now to further simplify, we're going to simply take this over, so we're going to subtract 649.74 from both sides. So we're going to have 4,002.6 joules minus 649.74 joules, and that is equal now to 0.01 kilograms multiplied by the latent heat of fusion of ice, which is what we're interested in. Next thing we do, we simplify here. So if we say 4002.6 minus 649.74, and we say equal, we're going to get this number 3352.6 0.86 joules. And that will be equal now to 0.01 kilograms multiplied by the latent heat of fusion. But since we want to find latent heat of fusion, we can divide both sides by 0.01 kilograms divided by 0.01 kilograms. And we're going to see that our latent heat of fusion, LF, will be equal to, so taking the calculator, we just divide by 0.01, and we get this number right here, 335,286 joule per kilogram, right? And that would be the value for the specific latent heat of fusion of ice. Okay, so now we can just move on to deal with our analysis. So in our analysis, we're asked a couple of questions. So the first, we say we need to define the specific latent heat of fusion. So we're going to say that this is the heat energy required to convert or to change, or let us say convert 1 kilogram of a solid, right, to 1 kilogram of liquid at its melting point. Right, so it's the amount of heat energy that is required to convert 1 kilogram of a solid to 1 kilogram of a liquid at its melting point. So in this case, in terms of the ice, the specific latent heat of fusion of the ice is just the heat energy required to change 1 kilogram of the ice to 1 kilogram of water at 0 degrees Celsius. Right, so that's the specific latent heat of fusion. Next up, it says here that it says why was the ice transferred quickly from the container to the styrofoam cup or the calorimeter. Now this was, so we could say now that this was done to ensure no heat from the surrounding was absorbed by the ice, or in other words, we could say to ensure the ice does not absorb heat energy from the environment or the surroundings. Now we know this is environment. Now we know that this might not be 100% preventable, so we try to move as quickly as possible to limit any possible errors. Right, now next thing, let's say now why was the styrofoam cup used in this experiment. So styrofoam has a negligible heat capacity, therefore it would not affect our readings. Right, so because of the negligible heat capacity of the styrofoam cup, it wouldn't essentially absorb any heat energy from the water, so all the heat energy that is lost by the water will actually go into the ice. Alright, now next thing it says now we're to compare the theoretical value for the specific latent heat of fusion of ice with our experimental value. Now the theoretical value for the specific latent heat of fusion of ice, right, is actually 334,000 joule per kilogram per Kelvin. Now our experimental value for the specific latent heat of fusion of the ice was, let's double check, it was 335,000, or approximately 335,000 Right, so I'm going to say 335,000 joule per kilogram per Kelvin. Right, so what we see is that we had a difference of approximately 4,000 joule per kilogram per Kelvin. Right, so the difference between the two was 1,000 joule per kilogram per Kelvin. Right, so that's the difference between both, and that could be due to certain errors in our experiment. So let's continue. Next thing we're going to do now is we're going to state some precautions. So the first one we could say is ensure the thermometer is read at eye level. Right, that's the first precaution. Next one, we could say ensure the ice is quickly transferred to the styrofoam cup. Right, now sources of error now. Right, we could say now that we could have some heat, or we could say the ice may absorb heat from the surroundings or from the environment. Right, so that's one possible source of error. Right, also we could have some, or we could say the temperature of the environment may fluctuate. Right, so the temperature of the environment may fluctuate, and that will actually now cause some instability in terms of our readings. Now, in terms of our conclusion, now we're going to just simply provide a direct response to our aim. Right, and our aim again, we can double check, was to determine the specific latent heat of fusion of ice using the method of mixtures. So what we're going to say here now is that the specific latent heat of fusion was found, specific latent heat of fusion of ice was found to be, right, we're going to quote the exact value, which is this right here, so 335,286 was found to be 335,286 joule per kilogram per Kelvin, right, using the method of mixtures. Right, and that would be our experiment completed. So again, Junior Roberts with realjuniorroberts.com. If there was anything in this video that you're still unsure about, please post it in the comments and I'll do my best to clear up any misconceptions for you. Like this if it was helpful, click subscribe and share so others are able to benefit. If you're currently doing physics labs and you need help, you could send me an email. I'll post information in the description for you to make contact. Thank you for watching.